Now if we have an object at distance O, focal length is f here, and again I seem to have the object looking like it's inside the focal length. We're going to assume that it's slightly outside the focal length. As the object moves closer and closer to the focal length, these rays, as we've seen, get more and more nearly parallel, and the focus occurs, or the image occurs, at a greater and greater distance. So that as the object distance approaches the focal length, the image distance approaches infinity. Now that's exactly what happens if we think about this equation. Okay? 1 over f equals 1 over O plus 1 over I. For a given lens, it has its focal length. The focal length doesn't change. The only things that can change for given lens are the object and image distances. Now, if the object distance was equal to the focal distance, you'd have 1 over f equals 1 over f, and that's it right there. 1 over I would have to be 0, which means that I would have to be awfully large, because when you divide 1 by a very large number, you get something close to 0. So as the object distance approaches the focal length, the image distance increases without bound. It approaches infinity, which is exactly what we see by tracing the rays. On the other hand, if the object distance is large, the image will form close to the focus, because 1 over O would be very small. 1 over I would have to be almost equal to 1 over f. Okay, now for a convex lens, the focal distance f is positive. We haven't talked yet about negative focal distances and negative image distances, but that's what we're leading up to. Okay? So f is greater than 0, and we have this. And as we saw just a minute ago, a smaller object distance implies a greater reciprocal object distance, which implies a smaller reciprocal image distance, which implies that I has to be greater. So the smaller O means a smaller object distance implies a greater image distance. And that implies, of course, a greater image size, because the image size is the image distance over the object distance. And this picture here shows us what happens if the object is at the focal distance. Then, by similarity, the rise and the run of this triangle here are equal to the rise and the run of this triangle. Since this ray passes through undeflected, then we see that these two rays have to be parallel. Since we have parallel rays or identical slopes, then the focus is at infinity. And that's exactly what we expect from the equation, which is kind of blurred here, but you have it on your notes. If the object is inside the focal distance, then what happens? Well, this corresponds to the magnifying glass. Remember, if we put the object, which is the f in this case, inside the focal distance, it's magnified, and as we move toward the focus, it gets magnified all out of proportion. You might be able to see that even a little better if I turn the lens around, because I can get it closer. Okay, the image gets bigger and bigger, blurs out, and then comes back inverted, as we've seen. Why does this happen? Well, if this is our object here, we have this ray going through and bending toward the focus, being directed toward the focus, and this ray going through undeflected. If we're inside the focus, then this triangle is going to have a bigger angle than this triangle. In other words, the angle here is going to be smaller than the angle here, and it's going to follow that this ray is steeper than this ray, which means that they're never going to converge out here. They're just going to keep getting further and further apart. So where do the rays converge? Well, if you extend the rays back here, and of course you don't really have actual light rays, but if you extend the rays back here, the rays converge at this point. So if you're looking from the other side of this lens, it looks like the rays that are coming from the top of the person's head are really coming from here, and that the person is both further away from the lens than he actually is, or that the object is further away from the lens, and also larger. Now, this image that appears to be there but really isn't, in other words, if you put a screen here, you're not going to see anything because the rays are over here. And if you put a screen over here, you're not going to see anything that makes sense because the rays aren't converging. But if you look through the lens, it appears that the light's coming and spreading out from this point, so it appears that the light is here instead of where it actually is. And that's what we see when we look through a magnifying glass. As the object moves closer and closer to the magnifying glass, the image moves closer and closer to the object, as you can see by tracing some rays. I'm not going to do that for you. You can work that out. And as we move the object further and further out toward the focal length, the image gets bigger and bigger and appears further and further away, until when we reach the focal length again, the rays are all parallel and everything appears to be infinitely large. We really don't see anything. The equation here relating the focal length, the image, and the object distances is such that the object distance is less than the focal length. In that case, the reciprocal of the focal length is less than the reciprocal of the object distance. Sorry, there's somebody knocking at the door and it's very distracting. Please go. Wait a minute, Shannon. I'm recording. I'll be there in a minute. Okay, excuse the interruption. I've got to ask people not to open that door for people who happen to be knocking. I've lost my train of thought. But we have an object that's inside the focal distance. The reciprocal of the focal length is then going to be less than the reciprocal of the object distance because the O is less than the F, so the reciprocal of the O is greater than the reciprocal of the F. That means that this thing is bigger than this, which means that this had better be negative if we're going to have equality. So now the image distance, the reciprocal of the image distance is negative, which means the image distance is negative, and that tells us that the image is on the wrong side of the lens. Okay? Looking again. Well, actually, no, we don't want to look at that right now.